Welcome back. So this is the second part of the Pascal's triangle. I'm going to do a few applications here just to show you how the triangle can be used for some applications, and some probably you will run into in your data management and probability course. So the first video with organized counting in Pascal's triangle, where I just introduced Pascal's triangle and then talked about some of the items, I'm going to put up a link up above there for you with regards to that. Now, for the applications component, I'm going to assume that you've watched that and you're familiar with Pascal's triangle and then how to find this triangle on its own for any nth row that you would like. So here are a few examples. Here's the first one. So this is a rather simpler one. Let's see if you remember the concept. So if somebody has asked you, what is the sum of the Pascal's 10th row? So meaning if you take all the items in Pascal's triangle for a particular row and you add them up together, what would the sum equal? So if you recall, so for instance, if we would take this, okay, so this is what it would mean. So for instance, let's say for the third row, okay, so for this one right here, the sum would be 1 plus 3 plus 3 plus 1, which would be equal to 8. And now we're asking for the 10th row. So if you remember, the Pascal's triangle, when you're going to be doing this, it's rather simple that the sum is always equal to 2 to the row itself, right? So to the nth row, which in our case would have been the 10th row. So this would have been 2 to the 10. So 1024. Okay, so that's what that would have been. So if we added up and summed up all of them. So that's a common sometimes question which is asked, right, on quizzes or tests that you will run into. And it's just a matter of noticing this pattern. And this pattern is basically that the sum of any row is 2 to the n. Okay, and we saw that actually in the previous video as well. So that's a simpler example. So here's a little bit more interesting one. So we talked about triangular numbers, right? So if we had coins and then we would just stack them up to create a triangle, which was basically planar. Okay, so it was in the plane. And we saw that, you know, the numbers that we would get, so depending on which one as we were going through, so 1 and 2 and 3 and 4 and 5, we saw that it was on the third diagonal, okay? Now, what if we started to stack things up? So like you can see here, and we started to create almost like a tetrahedral shape, okay? And these are called the tetrahedral numbers. So at first stage, so this would have been stage number 1, okay? So we would only have one ball, okay? So this maybe would have been the red ball right here on top. Then, okay, we want to be able to support that one ball, and we put it, okay, and then in order to support it, so that would have been kind of like the red and then the white that you see there. So you notice that on the second stage, so what we would have is, we would have 4 balls in total. So we would have one ball, right? Then we would have 4 balls. And then we would continue this pattern, okay, of stacking up. So now we could add up the gray balls right there. So the number of gray balls that we would have, so it would be 4 from the previous, which is already on top, and then adding up, so that would have been 1. So this would have been 1, 2, 3, and then it would have been 4, 5, okay, and then another, okay, so that would have been another one right there. So that would have been another 6. So in total, we would have had 10. And then we could continue this, okay, for each one. So this is asking, okay, so this would have been stage 1, kind of stage 2, stage 3. Okay, so the tetrahedral number for stage 3 is 10. And then the next one that actually follows is actually going to be, so this is going to be actually 20. So for that stage. Okay, so that's what we would have right there. So we can double check that. Okay, and then we would have, so we would have 1, 2, 3, 4. Okay, and then it would be 5, 6, 7, 8, 9. Okay, another 10, so that would have been 20. And now we can continue this pattern, okay, as we're going through. So, you know, can we find from Pascal's triangle what the actual next ones would have been. Okay, so for the number 5, of course, we can count up, because we can see the pink balls, but this is as far as we could go. So it would have been stage number 5. You know, how many of those pink balls there are, we would add them to the 20 that we have stacked on top of them. So that is fine. And then you'll notice that it would have been 1, 2, 3, 4, 5. Okay, then the next one would have had 4. Okay, then it would have been 3 plus 2 plus 1. So really, that's the pattern that we have in terms of stacking them up if we wanted to count them individually. So in total, what we would have had is, so this would have been 15 plus the 20. So in the stage number 5, or the tetrahedral number, so the 5th tetrahedral number would have been 35. If I go back here, so 1, 4, 10, 20, so 1, 4, 10, 20, and so on, what you would notice is that this, actually, interestingly enough, okay, notice 1, 4, 10. So this would have been going on this diagonal right here. And now, indeed, the next numbers, if we were doing them right here, I'm going to remove this from right here and just put it down a little bit, and then remove these dots and then the highlighter. So what we would have had is, if you notice, for this Pascal's triangle, so this would have been 1, 6, 15, right? 20, and then it would have been 15, 6, and 1. And notice, so this is it. So this is 1, 4, 10, 20. And now again, so we're going to be adding these up. So that would have been 35, right? And then we would continue this pattern on. So it looks like we are exactly on that 4th diagonal as we're going through all of these numbers. Now, they're asking us for the 10th one, okay? So that's a little bit annoying to try to get through all of them, but it's not going to be that bad. Okay, so welcome back. Okay, so there you go. So that's the 10th one right there. Now, you can certainly see that we do have a pattern, right? Like, because we're just adding these two up to get the number on a continuous basis, because that's how Pascal's triangle actually works, right? So that we just keep adding those up. You can find an actual formula for this tetrahedral pattern, but since we're only looking for 10, I just kind of went down the triangle to try to find it for us. And that's how you would be able to find that, right? So let's take a look at another application of this Pascal's triangle, or at least the method. And this method is actually pretty neat because you have it when you start doing and trying to find out paths. So using the Pascal's method to try to find the number of paths, and I'm going to provide you a couple of examples here, what I mean by these paths. So let's say we have a checkerboard, and this checkerboard, we want to be able to see how many paths are there all the way to the top. So we want to be able to get all the way, so either here, 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 and here. So in checkers, we can only go, okay, we'll go only on in a forward direction, so in this case upwards, so we can't go back, and we're only going to go on the white ones, okay? And then we can take kind of one step at a time, okay, in this checkerboard, assuming that there's no other checkers there that block us. So how would we do this? Well, okay, so the way that you can do it is you can count the number of paths. So you can either go here. Now there's only one way to get here and one way to get here. Maybe I'll remove that circle so that you can see the number. So that would have been 1, 1. Now you can continue going. So there's one way of getting to the next checkerboard. Okay, so this would have been 1, like this. But now to this next checkerboard, there are 2. There's one from here and then one from here. So there's 2 in total. and then going in this direction, there would be 1, right? So we're kind of going like this. So you're noticing what we're doing is we're just counting up. We're using what Pascal did, right? The other paths, and then adding them up together. Okay, so if I continue this, so this would have been 1. Now to get to here, there's 3 ways, because 1 from here and 2 from here. To get to this point, so again, there will be 3 ways. In this case, there will be 1. So you're noticing that we're kind of recreating this Pascal's triangle. And then again, now you're going to get stuck in here because you can only go one direction in here. Now in this way, we can go 4. Notice 6 and 4. Okay, so that's what this would have been. Now, to get to the next one, so in this direction, okay, so this would have been just counting, so there's only one way. So this is still stuck at 4. But to get to here, this would have been 10, because it's 6 plus the 4. And again, this is 10. And this would have been 5 right here, because 1 from here, and then 4 from here. And then you can continue, so this is still 5. Okay, now right here, so it's going to be these 2, that's 15. This right here, so that's going to be 20. This right here, so that's 14. Okay, so now right here, it's still only 14, so this would have been 34. Okay, adding those 2, this is 35, and then this is 20. So there are 20 ways to get to this spot. 35 ways to get to this spot, 34 ways to get to this spot, and then 14 ways to get to that spot. So if you want to know how many different paths to get all the way to the top, you can just add all of these up. So that would have been 20 plus the 35 plus the 34 plus 14. And then if you add all of this up, so 5 plus 4, which is 9, and then 13, carry the 1. And then we have, so 3, 6, 9, 10. So over 100 ways to be able to get to the top. And notice that we used just Pascal's triangle to try to see how those paths actually are created. So that's a checkerboard. Now, here's another example where you can do it with actually just paths. And you can imagine that these are streets and you're trying to get from one particular point to another point. And then you can say, okay, so how many different ways can I get there? And now we do have to make some assumptions. So here they tell us that we can only go to the right and down. So it's almost like saying we're going east and I guess south, right? If north is upwards. So to do this, you would create the same thing. So you would say, okay, so well, to get to this point right here, there's only one way to get there, right? Now, if I'm going only right and down, so now to get to this point right here, there are 2 ways, okay, because I'm going to be adding those 2 up. And then you can continue this. So this is, there's only one way here, okay? There's only one way here. Now you can go here and here. So that would have been 2 plus the 1, so there's 3 ways to get to there. Okay, so to get to here, so there's 2 ways to get to that point right here, and then 1 way to get here, so this would have been 3. And then again, so you can go from here to here, and you would have noticed, okay, this would have been 6. So that's pretty interesting that we can use that to create the number of paths. Okay, so in total here, there would be 6 ways to get from A to B. You can draw them out, of course, try to see like what patterns you might be able to create, okay, and then all the different ones. Or you can just do this and then find out how many different paths there are. Now, this can get more complicated because you can create a bigger and bigger grid, right? So that particular grid, you can just keep creating these and then trying to see, okay, so what's going to happen? So once again, you would start with 1. This would have been a 2, and then you can continue. So this would have been 1, okay, 1, all the way, 1, okay, 1 way to get all the way there, if it's only down and to the right, and then you can continue this pattern. So, to get to this point, this would have been now 3, okay, so 3 different ways. Again, to get to here, well, it's 3 plus the 1, so this would have been 4 different ways, okay, to get to here. To get to here, this is 4 plus the 1, so that would have been 5. To get to here, this would have been 5 plus the 1, which is 6. And you can continue this, right? So this would have been 1. Now to get to here, down, this would have been 3. And then from here, so now this is 3 plus the 3. So notice that's going to be 6. This is going to start growing on us pretty quickly. 6 plus the 4, which is 10. Okay, this is going to be 15. It's going to be 21, and you'll notice that these numbers are kind of resembling what Pascal's triangle would have been. And you can continue this, you know, so again, so there's only one way, and then coming down here, so this would have been 4, right? 4 plus the 6, 10. Okay, this would have been 20. I'm just adding them up now. This is 25. Now, this is starting to get pretty big, so 25 plus the 21. So this is, I guess, 46. And then you can do and finish the last one as well, right here. So that's 5. This was 10, so 10. And then the 5, so that's 15. This is 35. Right, so this would have been 35 plus the, I guess, 25. Okay, so that we had there. So that would have been 40, 60. Okay, and then you can add those up. So I guess that's 106. Okay, and you can of course check it. But I wanted to give you the gist of like how do we go about trying to find the number of paths. And we are restricting. You can only go to the right and down. So these are several applications of Pascal's triangle that you probably are going to run into, or at least I hope you will, in some way in terms of counting things up. So counting paths, right? We've done here the tetrahedral numbers. That might come up at some point for you. And I think these are kind of useful to be able to see and then apply them utilizing the Pascal's triangle. All right. Thanks for watching. We'll see you in a future video. Bye, everybody.